Having the opportunity to design a lab from scratch, start from an empty room, and in our case, roughly 10 months later, have a beautiful functioning lab with cold fridges, many qubits, lots of control hardware, and of course, very importantly, happy and excited students and researchers. That's really one of the big pleasures of being a professor. My name is Morten Kjaergaard. I'm an associate professor of quantum information physics here at the Niels Bohr Institute at University of Copenhagen. So quantum information science is in some sense the combination of quantum theory and the science of what is information or what is computing. And I've always been interested in both. Since I was a kid, I was into computers. Then I started university, I learned about quantum theory. And so when I learned that there was a combination of the two, it somehow seemed like exactly what I wanted to work on. And the work we do in our team specifically is spread into kind of two different sections, both within superconducting quantum computing. One is focused on developing interesting new types of qubits, understanding materials, and understanding how to build better qubits or different interesting qubits. And the other half of our work is focused on, okay, now let's say you have 5 qubits, 10 qubits, understanding basic quantum information questions using superconducting qubits is really the focus of a lot of our research. So a large part of our work is also focused on, let's say you have a couple of qubits. What's the right way to characterize those qubits? There are many ways to do it. Many ways of them are very well established, but there's still kind of fundamental questions about what is the right way to characterize, quote unquote, the quality of qubits. Our team works very closely with Professor Will Oliver's team at MIT. We have a big joint program together where the idea is that we're establishing parallel labs at MIT and here in Copenhagen, where we use the same technological backbone. So the same kind of, for example, Bluefors XLD cryostats, the same kind of control hardware, but crucially also the same control software. This means that we can send students back and forth, we can co-develop device designs and make everything modular across multiple sites, and thereby really work together. And especially in the beginning, we are learning a lot from the MIT side as we're building up also capabilities here. So over the last year, we've built up a new facility here with 2 Bluefors fridges, an XLD 400 with 65 coax lines, and an XLD 1000 with just over 100 lines in. And these are systems that we use to explore these multi-qubit processors and these fundamental questions in quantum information science. The cryostats have been incredible to work with. They reach less than 10 millikelvin temperature right off the bat, even with a lot of components inside, so we're very happy with that. The systems are incredibly stable, and in this, specifically within this research area of, let's call it high fidelity superconducting quantum information systems, reliability is really the name of the game. Things need to be reliable and dependable. And so far, our new generation XLDs and the new generation gas handling systems have really been fantastically reliable and done exactly what we wanted, exactly when we wanted it. Building up a sophisticated modern lab is, of course, not something one person can do. That's a big team effort. So we had 3 or 4 PhD students and a couple of senior researchers working almost full-time on thinking through every single cable, every single connection, even designing the tables specifically so they match the room and all this stuff. So that takes a lot of care and attention to detail, and been very fortunate to have a large team of students and researchers who care about these things together with me. I'm very excited for the students who have now spent a long time building up this incredible lab space to get into the nitty-gritty of controlling qubits, controlling many qubits, and really understanding the many-faceted nature of what it means to operate and orchestrate multi-qubit systems. There we have a number of interesting experiments that we have been ready to execute for a while, and now that all the hardware is there, the fridges are cold, the qubits are cold, we're really quite excited to get cranking on that.